Hello all. In this video, we will continue our discussion on these select laminas that we have started in the previous video. In previous video, we have discussed about these special and general orthotropic laminates, and we also discussed about symmetric laminates. In this video, we'll be looking at few other laminates starting from Angleply and the crossply laminates. Later we will discuss a few more details about the symmetric laminates before we go to these anti-symmetry, and lastly we will also discuss about quasi-isotropic laminates. So before we proceed, again a quick recap about the Q matrices. So these are the Q matrices we get for principal material directions, meaning if the laminate or the lamina is oriented along the principal directions, which are along the fibers and perpendicular to the fibers. So this happens when your angles theta are 0 or 90 degrees. Then we have these Q16 and Q26 going to 0. But if we are talking about off axis, meaning any angle between the 0 and 90, then we have to use this transformed stiffness matrix Q dash, where we notice that Q16 and Q26 are no more 0 like in the stiffness matrix shown here. But in last class, we also mentioned what if there are two lamina, both were made of the same material, same thickness, but the only difference is they are of two different angles, plus alpha and minus alpha. So we said in that case, the there are four terms which remain same. So meaning this Q11, Q22, Q12 and Q6. These four terms, there is no change because they had the even terms of sine and cos in those expressions of Qij's. But when we come look at Q16 and Q26, we notice that the magnitudes are the same, but there is a difference in the sign. So this we are trying to emphasize here, because the moment we look at some special laminates, we will use this property to show that some of the couplings are either existing or non-existing. Okay, so let's start with Angleply and crossply laminates. So first let's look at what they define, starting with Angleply laminate. So here again we are talking about all the laminas made up of same thickness and same material. The only difference is we are saying that all of them are have only one angle, either it is plus theta or minus theta. Meaning, let's say if this theta is 30 degrees, all layers in this laminate are either 30 or minus 30. So for example, I could have written it as 30, minus 30, minus 30 and minus 30. This could be a laminate sequence. Since it only has 30 and minus 30, then we can call it as an Angleply laminate. Okay. Next we look at what we call it as a crossply laminate. Here again we say they are of the same thickness and material, all layers are of same thickness and material, but the orientation angles are either 0 or 90. So for example, I can write it like 0, 0, 90, 0. So this is a crossply laminate because it only has two angles which are 0 and 90. And if we recall the previous, will we be using Q or Q dash for a crossply laminate? For a crossply laminate, we will be using Q because the angle is either 0 or 90. But what is the specialty of using Q? We know that the Q16 and Q26 terms go to 0. When they go to 0, we know that the corresponding terms in the A, B and D matrix also go to 0. So which include that A16 and A26 go to 0. Similarly, B16 and B26 terms go to 0, and similarly D16 and D26 terms, they all go to 0. So meaning it, some of these couplings like the extension shear coupling or the bending twist coupling, they are not existing in a cross-ply laminate, solely because we are only focusing on either 0 degree or 90 degree. Next, we look at a definition for balanced laminate. So these are laminates in which you have an equal number of theta and minus theta. So this angle theta could also be 0, 90, but as of now we are saying, let's say we are talking about all the layers are made up of angle 30. Then we are saying it has equal number of layers with angle 30 and the same number of layers are there for minus 30 orientation. So in this again we can discuss about Angleply and crossply. So we can start by saying what do we mean by a balanced Angleply laminates? Balanced, we have just shown that it should have equal number of theta and minus theta. Angleply, we know that the angles should be only theta and minus theta. So for example, I can write it as, let's say, 30, 30, minus 30, minus 30. Here we have 2 with theta is equal to 30 and 2 layers with minus 30. So we have, so first it is an Angleply because we are only having theta and minus theta, which are 30 and minus 30, and it is also balanced because it has equal number, like there are 2 with plus theta 30 and 2 with minus theta minus 30. The same definition we can also apply for cross-ply laminates, where the cross-ply meaning it should be only 0 and 90s, and balanced meaning it should have equal number of 0 layers, 0 oriented layers, and equal number of 90-degree oriented layers. So again I can make up an example, something like 0, 0, 90, 0, 90, 0. So here we have 3 layers with 0 orientation and 3 layers with 90 orientation. So it is balanced, and it is cross-ply because all of them are either 0 and 90 orientations. Okay. There is one more important observation we have to see, starting looking at the A matrix. So in the ABD matrices of the classical laminate theory, this is the expression for writing the matrix A. So here Q is the transform stiffness matrix, and what is Zk minus Zk minus 1? So if you look closely, so earlier we said if this is the mid surface and this is a particular layer, we said this bottom layer is represented with Zk and this top of the top surface is represented with Zk minus 1. So what is the difference of Zk minus Zk minus 1? It is simply the thickness of this layer. So let's say this is Tk, meaning the thickness of kth layer. So essentially we can write this Aij is summation of Qij for the kth layer times the thickness Tk. So the point I am trying to make here is, now let me ask you a question. Will it matter what is the real sequence of the layers? Meaning, let's say there are 3 layers in this layer. So let's say these are 0, 45, 30, now 60. This versus, let's say we are talking about another laminate which has the same 3 layers in a different sequence. Let's say 45, 60 and 0. Now the question is, will these both laminates have the same A matrix? The answer is yes, because if we look at this expression for A, we said it is summation of Q matrix times the thickness. So where does the sequence come into this expression? The sequence comes in by taking care of this Zk minus Zk minus 1. But since we are simply replacing it with the thickness, it doesn't matter. So for example, in the first case, how can we write the A matrix? Let's say Aij will be Qij for zeroth layer, zero orientation times, let's say, thickness of the zero layer, plus Qij for the orientation 45 times the thickness of 45, plus Qij bar for the 60-degree orientation times thickness of the layer with 60 orientation. So this is for the first laminate we showed, and for the second laminate it is the same, but we'll see the sequence is different. So Qij for 45 times thickness of 45 plus Qij of 60 times thickness of 60 plus Qij, sorry, Ij of 0 times thickness of 0. So we notice that uh, this Aij is written as sum of three terms, and for both the laminates these three terms are the same. The only difference is the sequence of the terms has changed. So essentially what we are trying to say is, for the A matrix, is independent of the sequence. And we have shown the reason why it is independent of stacking sequence, because this term, the zk minus zk minus 1, uh, signifies the thickness, and it doesn't matter whether the thickness is coming from the bottom layer, top layer, or too far or too close to the mid surface. The thickness value will remain the same, so it is independent of the sequence. But we cannot say the same for B matrix and D matrix because they are far. I mean, you have the z square and the z cube terms, which are not like the thickness. There it really matters how far it is from the mid surface. Okay, now let's move to the symmetric laminate, which I have already discussed. So earlier we said we call something as symmetric laminate when there are pairs where they are made up of the same material, orientation and thickness. These are symmetric about the mid surface. So let's say here is a pair shown in the figure. If they both have the same thickness, same orientation, and they are made with the same material, meaning your Q matrix is the same, and if this applies for all the layers in the laminate, then we call it as the symmetric laminate. And the reason why symmetric laminates are preferred in manufacturing is because it is easy to analyze, and second, there is no tendency to bend or twist during curing, because during curing there is an extension or shrinkage in the material. Because of this shrinkage, we don't want the shape of this composite to change. But if there is the B matrix is non-zero, then there is a change in the shape, because then we have this extension bending coupling coming. So the most important point here is the B matrix goes to 0 for a symmetric laminate, and this we have already shown in the previous video. The reason why we are looking at here is to discuss it in the context of Angle-ply laminate. So now let's see what we term it as a symmetric Angle-ply laminate. Angle-ply, as we already mentioned, uh, these are made up of these either theta or minus theta. And the additional condition we are now having is it should be symmetric. So let's see with an example. So let's say it is plus minus 45 times minus 45, and it is symmetry. So if I expand this, it should be plus 45 minus 45 minus 45, and since it is symmetric I need to mirror it up, so it should be minus 45 minus 45 and plus 45. So this is one example of a symmetric Angle-ply laminate. So of course we can come up with many other examples in a similar fashion. And regarding the symmetric cross-ply laminate, Here the only difference is instead of theta we'll be using 0 and 90. So let's again look at an example. Let's say 02/90 and it is symmetry. So if I have to expand, it will be 0 0 90 90 0 0. So the point we are trying to say here is we call this as a cross-ply because all the layers are either 0 or 90, and we call it as symmetry because about the mid plane, here is the mid surface for this here, and about this mid plane it is symmetric, meaning this theta 90 and 90 and this 0 and 0 and this 0 and 0, they are all symmetric about the mid surface. Now that we have seen these symmetric laminates, now also let's also see at the antisymmetric laminates, which are closely related. So as the name says, it is not just symmetry, but there is an antisymmetry. Let's see what it is. So the definition is very close to a symmetric laminate, saying that it has identical ply material and thickness about the mid surface, meaning both of these will have the same thickness and they are made up of the same material. Let's say if this is CFRP, this is also CFRP. But the only difference is the ply orientation are antisymmetric. What do we mean by orientations are antisymmetric? Meaning like if one of the layer is plus theta, the other layer will be minus theta. That's the only difference. So this applies for all the layers in the laminate. So as an example, we can see something like this, saying that 45 minus 30, 30 minus 40. So here we see that this minus 30 and 30 are anti-symmetric orientations, and similarly this 45 and minus 45 are again anti-symmetric orientations. The what is symmetric here is we are assuming that they both these 45 and the minus 45 are made of the same material and they are of equal thickness. The same goes with these layers minus 30 and plus 30. So let's look at another subcase where we are discussing about antisymmetry angle-ply laminates. We call it as angle-ply if all layers follow one single angle, either theta or minus theta. So for example, I can come up with something close to that, 30 minus 30, 30 and minus 30. Here I can call this as an angle-ply because all angles are either 30 or minus 30, and I will call it as an antisymmetry because the middle two and the extreme two, the angles are anti-symmetric orientations. Okay, but let's see how this antisymmetric angle-ply laminate affects the ABD matrices. For that, first we will notice what happens, how does the transform stiffness matrix get affected. So at the beginning of this video, we just revised this, saying that the Q matrix terms Q16 and the Q26, the magnitude wise they are the same whether the angle is plus alpha or minus alpha, but there is a change in the sign. Similar, the same goes with Q26. So let's see how this will affect our ABD matrices. So because of this change in sign, what happens is, let's say we are discussing about this example again, the first layer plus 30. So let's focus on this first layer and the last layer. First layer and the last layer, the thicknesses are the same. So let's say if you are talking about writing the A matrix. So let's write it here. Aij we said is summation the Qij terms times the Zk minus 1. So we have just shown that Zk minus 1 will be the thickness, since both the top layer and the bottom layer have the same thickness. We need not bother about these Z terms. we only need to bother about these q terms. But in q terms we said if we are writing it for qij plus alpha, or in this case it is plus 30, and we need to add it with qij of minus 30. So this is for aij. But if we are focusing for only a16, we notice that these two values are equal and opposite, meaning they will go to 0. Similar thing we can show it for a26 as well. But when it comes to the D matrix, there too we can show that since Z has a cubic terms, even this Zk minus 1, or in other words Z cube minus Zk minus 1 cube, that will also be constant for the top layer and the bottom layer. And because of this relation for these Q16 and the Q26 terms, even the D matrix terms go to 0. So these are all required because, as we know, this has some physical significance, like A16 and A26 going to 0, meaning the extension shear coupling is gone. So therefore, if you are applying forces, there is no bending in the laminate, meaning that if forces are applied or normal forces are applied, there is no shear deformation in the laminate. Similarly, this D16 and D26, we call them as the bending twist coupling, meaning when there is a bending movement applied, then there is no twist happening in the laminate. Okay. Now let's move to the last of these laminates we are discussing, which is the quasi-isotropic laminates. This is an interesting laminate because though we are starting with an orthotropic material, meaning that the properties are different in different directions, there are certain sequences where we can get a quasi-isotropic behavior. So we are saying it is just some kind of isotropy. Don't think that it is the same isotropic like in aluminum or steel, but we are saying there is a small sense of isotropy, and let's see what is that small sense. So we can get these quasi-isotropic laminates not with every orientation but for some specific orientations. And here are the conditions for those orientations. First, it should have 3 or more orthotropic lamina with the same material and geometry. Meaning the same material, we know what it means, geometry meaning the thicknesses are the same. But the angles are chosen in a specified fashion, and the angle between the adjacent plies is given by this theta is equal to 180 by n, where n is the number of plies. So let's say if n is equal to 3, then this theta will be 180 by 3, which is 60. So I can come up with a laminate sequence something like this: minus 60, 0, 60. So as you can see here, between two adjacent layers, the angle is always 60. Similarly, looking for n is equal to 4, theta will find it as 180 by 4, which is 45. And one of the combinations we can come for a quasi-isotropic laminate with n is equal to 4 layers is, let's say, minus 45, 0, 45, and 90. So now let's get back to the definition of quasi-isotropic and see what we really meant by that. Here we are saying that the in-plane properties are isotropic, meaning the, let's say, the stiffness along the x direction or the y direction in the plane of the laminate are the same, or in any other direction are the same. But the out of plane properties, there is no, we cannot comment on the isotropy. So this is possible if we get this A matrix to be isotropic. Let's see what we meant by A matrix to be isotropic. Here we are saying this A11 term and the A22 term are the same. And similarly, A66 term, we are able to write in terms of just the A11 and A12 terms. If you recall, this is exactly the form of a stiffness matrix we had for a isotropic material, where we had these diagonal terms, the Q11 and Q22 are the same, and Q66 is written in terms of Q11 and Q12. That's the reason why we call this, it is isotropic in the plane. But as I already mentioned, the B matrix and D matrix, they may not show any isotropy. So because we only call it quasi-isotropic because of this A matrix showing this isotropic form. And there are applications when this is of use. Finally, let's summarize what we have discussed till now. In the earlier video, we already discussed about the special and general orthotropic laminate. These are essentially a single layer, either with orientations theta is equal to 0, 90, which we call it as the specially orthotropic laminate, or theta going somewhere in between 0 and 90, then we call it as the general orthotropic laminate. The only difference is either we use the stiffness matrix versus the transform stiffness matrix. In this video, we started by discussing what we meant by Angleply. We said if they are made with the same material and same thickness, the only difference is the angles are either theta or minus theta. Then we call it as Angleply. For crossply, we said the angles are either 0 or 90. But later we also discussed about this balanced Angleply and the balanced crossply laminates, where we said there are equal number of thetas and equal number of minus thetas for balanced Angleply, and for balanced crossply we said there are equal number of 0-degree layers and the 90-degree layers. For symmetric laminates, we said the material, thickness and the orientation. If we have a pair where all of them are the same about the mid surface, then we call that as stiffness laminates. The major advantage is the B matrix go to 0, which means there is no coupling between extension and bending. And then we also discussed about these anti-symmetric laminates, where we said things are symmetric with respect to the material and the thickness, but the angle wise they are either theta or minus theta. So we are talking about pairs about the mid surface. And because of this definition of antisymmetry, we said there are at least two important couplings which are not existing. These are the A16, A26, which bring in the extension shear coupling, or the D16 or D26, which bring in the bending twist coupling. And lastly, we also discussed about this quasi-isotropic laminate, where we said in the plane of the laminate we have isotropic properties, meaning let's say the stiffness is the same in all directions in the plane, but which also means that the A matrix takes a form which is of an isotropic material. But we cannot comment on the B and D matrices, they can have any other form. So this should summarize the generally commonly used laminates which are used in the industry. And as we have shown, the reason why sometimes we choose one of these, because there are some of the couplings which are non-existing, and these are of use not just in the analysis but also in the manufacturing. Like for example, symmetric laminates, we said during curing we don't want the change of shape in the laminate, then we should use the symmetric laminates where this coupling of bending extension is gone. Okay, this should conclude our discussion on the select laminates. Next video will briefly look into what is the hygrothermal stresses in a laminate.